Okay, now it's audible. Am I right? Okay, so let's start with the session. I'll just share my screen. So yeah, let me just know whether my screen is visible. Okay, so if everything is fine, let's start with the session. So yeah, without any delay, I would like to start here. Yeah, today we'll be having the session 1 out of 60. So where I'll be covering CA master course on CA. Okay, let me introduce about ourselves. So we are Technocraft Academy. So we provide trainings on computer applications, spoken English, CAD CAM CE, and also along with that, we provide the trainings on data analytics and full stack development. Yeah. So along with this, we also provide the 100% placement for the students who are going to join our institute. If you want more information, please do contact us. So the number is given. So you can even mail us. Yeah, so I'd like to introduce myself here. I'm Yogesh Dhanwadi, corporate training head at Technocraft Academy. I'm handling mechanical as well as CAE, full stack, and full data analytics course. Yeah, so without any delay, I would like to jump into the today's session. So let's say if you want to get into CAE field, what exactly you need to do? So if you're a complete fresher, so how you can start your career. So for that, I have a roadmap here. So before that, you can see here there are types of industries. So you need to go through that. The first one is the tier 3 industries. In that, we'll be having the raw and semi material, where these tier 3 industries will provide the raw as well as the semi raw materials to the tier 2 and tier 1 industries, and then they will utilize it and they build or they manufacture the components for the automotive industries or medium scale industries. So next one we have the tier two industries where what exactly they do is they are just non-automotive grade parts and the systems they will produce. In short, they will provide it to the tier one industries. So what exactly tier one industries? So they will manufacture the automotive parts, not the complete uh, car or uh, the industrial equipments. They will provide the subcomponents and the parts, the casting components. Yeah, these things they will provide. Yeah, we'll say about the OEM. So what are they? So from tier 3, tier 2, tier 1. So they will get all the relative information and the parts, castings, sub-assemblies, okay, sub-components. They will take everything. They will assemble and they will manufacture the original equipment. They are the original equipment manufacturers. Yeah. So examples for the tier three industries, you could see we have the UMC and SMC. So these are the globally I had just taken. So you can consider all the tier three industries. If you Google it, also you'll get to know what are the industries available in India. So when it comes to tier two, you could see we have the NXP and Renaissance, and we have the ANSA. When it comes to tier one industries, we have the Bosch show, which will provide all the you can say the motors, yeah, few mechanisms. So all the parts and sub assemblies will be given to the Bosch. So there are a lot of things you can just check into that. So they are the partners for most of the OEMs. Yeah, and then even we have the Valio, Continental is for the ADAS. Yeah, in India we can actually say that. So we have the ZF. When it comes to OEM, so we have the Volkswagen, GM, Toyota, Honda, Ford, Mercedes-Benz, Daimler, Tesla. Yeah. When it comes to Indian market, we have the Tata and then Mahindra and Mahindra. Okay, Suzuki, we have it. So Hyundai. So these are the OEMs we can call it. Okay, to build a particular car, they'll be having a lot of connections and the contracts with the tier one, tier two, tier three companies, and they get all the relevant information and they manufacture a medium industrial equipment or else the complete car or truck or bus or whatever it is. Yeah. Now, why we need these industries or why we need the tier one, tier two, tier three industries when it comes to we have the OEM, they can do everything by themselves, right? So they can manufacture. So why they need to connect the correct? So when it comes to this answer, so why they outsource in short, they want to see the cost. Okay, let's say if you want to hire someone, assume if you're working in TCS, Tata Consultancy, or if you're working in Mahindra, they need to pay you, right? And then you are a permanent employee of that company, right? So instead of that particular permanent employee, what they can do is, let's say if you're into CE, they can even go to the uh, service-based companies like you can say CREO, we have it, Citadel, okay, for the CE, okay, a lot of service companies, they will just hire the candidates who can support OEMs to do their activities, especially for this webinar. If they want to do the modeling activities and the for the crash and NVH, define the contacts, conditions, everything, they will do it. Okay, what they do is they outsource this. For example, digital, yeah, for them they uh, outsource it and they will mesh the component without any issue. Biometrics everything will be done. They will give us that's for the OEMs in short. Yeah. So what exactly they do? Though, so these activities, that are not that important for them. So let's say I want to run the analysis and give the results. Okay, when it comes to OEM, it is important for them to mesh the component, do the contact checks, everything, and waste the time, right? So only focus on the core competencies. Always do the analysis, validate it, and give the decision, and then make the decision and then manufacture the component. Yeah. Very important thing again is the speed and scalability. So what they can they can get on the that is important, right? Yeah. So now we'll focus on next thing. If you're a freshman, you need to start your career. So as I explained, so you already got to know about industries. Right? You're going to get OEM. So if you want to target for the OEM, so you already got to know how much experience you should have it. Yeah. Now, what are the career options you have it now in respect to the domains in CA? Let's focus on that. First one is the we have NVH domain. Okay, in CA, the noise and then harness, yeah, and the vibration, and then we have the durability, yeah, and then we have the crash analysis, optimization, multi-body dynamics. We have the thermal analysis. We have the C. These all are the options which are available for each and everyone. If you are doing the 2 years experience, like if you're a fresher, you can choose any of the domain here, any of the analysis like that. Like I want to become an expert in NVH, whereas I want to become an expert in durability. You can focus that field and start your efforts. So that definitely one day you'll be, get hired for that your responsibilities and well, let's see about the durability in short. I would like to take you through few of these domains. Let's see that. When it comes to durability, you could see what you need to do. First thing is you need to check the static life of the component. Correct? How many years that component going to work? Right? Let's say if you consider a simple cycle. So if you consider a pedal crank, right? How many cycles that particular pedal crank can go through? Yeah, and you need to analyze it. Similarly, for automotive components also, there will be a lot of components which you need to do the durability analysis. You need to check the pre-passes, how exactly it is going to generate the crack out of it, the spot, and how you need to rectify that. You need to optimize it. Yeah? And then fracture mechanism, if it is going to fracture, how the crack propagation is going to happen. So when it comes to the durability, structural durability, you need to consider. So for the tools, we have ANSYS, Abaqus, Nastrin, creep analysis, we have the Abaqus again. So fracture Abaqus again. So ANSYS also can consider the structural durability of the Abaqus. So I'd like to conclude here. If you want to get into durability, where you focus on the Abaqus, LS-DYNA is the most important software. So LS-DYNA is for the current in short. Yeah. So you could see these are the physics. When it comes to fatigue life, we have the stress analysis and the material behavior. And for example, fracture and the material damage mechanism you should consider. Yeah. Similarly, for others, you can see. Due to time constraint, I would not go through all the then you can try to understand it. We can focus on more content today. Now, let's see now about optimization. Very important topic. You can see optimization. We have the group optimization. We have the topology. We have sensitivity analysis. We have the multi optimization. Okay, assume you have a component. Uh, AIFT cranks or knuckles, whatever it is. You have designed it if it is weighing around 8 kg or 8.5 kg. That weight might not be needed. So with that, let's say if you're working with the OEMs or any of the home scale industries, if a particular component or part is weighing that much, and if it is adding a lot of mass and you can do mass with that, you can you can what you can do is if you run the topology optimization and shape optimization as well as the sensitivity analysis to reduce the mass of it and also improve the performance of the component. Also, let's say whatever design you might have done, that design might not be optimistic to withstand that particular load, which is shape and sizing. You might even achieve same requirement with less mass also. That you can do it here. Okay, there are things when it comes to optimization and recommend of this part. If you're working the small scale and the medium scale, I recommend you to use SolidWorks. but most predominantly struct will be used in short. Yeah. So you could see the physics behind it. So we can refer it later also. Let's the crash. Yeah. When it comes to crash, you could see there are a lot of things you can do under the crash. You want to get it very difficult for you. So you need to start with any of the other domains and you need to gain the knowledge out of it. So I'd like to go through everything. See, year of cache we have it, and we have the crash. We had also couldn't able to handle the crash. So one of the memory had fallen on the wall also, and the entire family died. Right. So same thing, occupant safety we have it. Heat analysis, fear impact. Okay, and then we have the side impact, child safety also, and then the EV battery simulations, the car impact, the bumper, petrol. So a lot of analysis is there, even front impact. So these all the analysis, and then we optimize the car. Then based on that, we get ratings, right? We have ratings, so cost and these all things are very important. I hope you got to know about few things about these all the domains. So I'd like to go on with it and first study accordingly, gain your experience, and get into the field if you're a fresher or you need experience. Yeah. Now let's start looking at the fresher wise. So if you're a fresher, then we can start on to OEMs or Tata or Mahindra. For example, if you're an Indian, you are working in other countries also. Let's say target the biggest the Toyota, Suzuki, Mercedes, right? BMW. So if you want to get into these as a fresher, quite difficult. So if you are from the top universities, you have these, get these GE it is. But if you're a student of any of the local universities, very difficult for you people to get into it. So you need to gain the experience. Now, what do we do? You need to set a strategy and a basic framework for that. So how? First, know about yourself, where you're standing. Okay. If you're a mechanical, you can consider any of aeronautical. Yeah. So where you're standing, what are the basics of it? What is the fundamentals you're having it? You don't know anything. Even you can start from scratch. Also, can refer the strength of material. Yeah. Song, down. These all you can refer and you can build your basics. Or else you can do MTech also. If you're a graduate, you want to do all that. Can even do the masters, but right now I might not recommend you to do the masters abroad. The situation is not that good. People are doing the masters, but they're not getting job again. They're coming back to the India with a lot of hefty loans. So if you want to go to abroad and you might need around 40 to 30 lakhs or more than that, even 60 lakhs. How come you want to have it? Loan, education loan, or whatever it is. If you are by chance, okay, 99.9% you might get a job, but if not, then you're lying. Better you focus on the tools and study accordingly. I would recommend you first strategize yourself. Okay, let's say you don't know anything, go through basics of CAE fundamentals. You refer some term, everything you refer, know about resistance, know about the mechanical properties. Okay, what are yield strength, what is stress strain curve, okay, elastic uh, strength, okay, stiffness, hardness, everything, okay, each and every basic related to the mechanical industry, just go through that. Now, let's say if you want to get into CA field, I would recommend to become a CA model do that. But how you can? First and foremost thing is you can learn ANSA and HyperMesh tools, also HyperBox. So ANSA is basically for pre-processing. Most of the OEMs use ANSA and HyperMesh to mesh the model and define the connections, compacts, more models. Yeah. So for that, you can just start your career with this. Okay. But in OEMs, you not need to because you just need to take that model and do the practicals and make the decisions. But right now, you can't get into that. But you can start with this. Well, so what exactly you're gonna achieve with this? You're gonna gain the experience with CA and also you can explore this basic structural analysis, buckling, durability, yeah, and then heat transfer, safety. You can explore each and every division and learn accordingly. Okay, if you have these tools, you can even get into the service-based companies like the Citadel, XPO, a lot of things are there, even these which Accenture, Capgemini, TCS, service-based companies, they will simply consider hire you as a CE modeler. Yeah, as I recommended, ANSA and HyperMesh are the tools which you need to know. Yeah. Now, back to you. So, if you're a complete fresher, they may even offer you 3 lakhs, 4 lakhs, not more than that. 5 lakhs. You can get up to 6 lakhs if you're from good uh, university, and if they are going to hire you with respect to the placements of particular industries and universities, then you might get the better package also. But don't worry about the package up to 4 years in your life experience. If you're in the top industries or the top, sorry, top colleges, you can expect 3 lakhs or 20,000 or 18,000 is the max that you might go for at least a couple of years. Next, CAE analyst. So once you become a CA modeler, so you might do the CA activities like reporting, measuring, connections, mapping, then explore NVH domain or durability or factor optimization. I would recommend NVH is the easiest one. Then you can refer durability. And also you can do it. It will take some time, but you can achieve the expertise in it. Now, so how do we get the what experience in NVH durability in Flash? It is not available in the market, right? So if you go into any of the courses available in the market, any of the training providers, CAD centers, and not going to name any of the training centers, they'll say what is structural analysis, what is stress, what is training, take a simple model, apply the information here, get the result, extract it, deep dive into it, but it's not going to help us for the OEMs, right? Basics each and everyone can when it comes to OEMs, they need a lot of expertise in these domains. Yeah, what exactly are. You need to have the practical examples of automotive components, durability, crash optimization. They might not have it. If they have it, that would be nice. But if they are not, please try to find a right institute or else right YouTube channel or else refer some of the uh, resellers. Let's say ANSA, reseller, beta C, you can directly contact Alpha, directly go and learn with us. But the cost is very high. If you want to learn only ANSA, they might charge you, I don't know, but approximately, I'm just guessing the figures, guys, it is 70,000 or 90,000. I don't know. If you want to learn for free, you have given that, or if you want to learn completely, even charge less. But even so, if you can go there with the group of team from the company, they might even charge less. They might not even train you guys if you're outside. They are having the contact with companies and give the trainings to. Yeah, so this is about CE analyst job role. So what you need to do. The next package is 5 to 8 lakhs. So let's say you already know the CE modeling activities, and if you want to get into CE analyst, while you were a CA modeler, if you had learned these all things, you might expect up to 8 lakhs also. Sure. Yeah. Very easy. So now, after this, what is the next option you have it? Option three. Let's say even though you might not gain these knowledges or yeah, you want to join a company very quickly and do things. can start with the resellers, CA consultant. Let's say explore the what you can say. Let's say we have the SolidWorks resellers, we have the NX resellers, CREO, and then the raw system, yeah, and the Autodesk Inventor, and these all the simulation tools are there. You can refer to any of these resellers and get into there, work as a technical support engineer, pre-sales, or training consultant, whatever it is. There are a lot of opportunities to visit industries, learn what they are doing, and execute their requirement, train them, get information to solve their issues. This will give enormous amount of knowledge for you guys. Yeah. So let me take. Yeah, I think with this, what you can do is you can achieve the domain knowledge and you can replicate it to OEMs also. I would recommend. So when I came from these days, I'm from the same field, guys. So what I did is I joined the uh, SolidWorks reseller, and then I got the experience, and then I worked the same domain for a couple of years, and then I went into it. And yeah, this is the good opportunity for me also, and for you also. I recommend the same thing. Yeah, I'd like to take a couple of minutes break so that we can just jump into the next thing. Manisha, देखो होगा मिला? Yeah, sorry guys. So let's start with this. Next one is to deal with the CA modeler. So let's say if you want to become a CA modeler, and if you're asking me what would be the skills I would like to have it, and what would be the average package. So I have already mentioned, guys. I explained the slide also before, right? Will be 3 to 6 LPA, and on an average, you might achieve 4.5 LPA. Later, it might go up to 0, but if you're working with the same service provider, it is quite difficult to achieve that. So you need to switch often. So to tell this, but you should, yeah, skills required. So first thing, if you want to practice the model, you should know the basic fundamentals. And then you also need to know about the modeling, meshing for the 2D shell components and the 3D components. Also, connections and contact creations, morphing, user integration, creating includes for the sub-assemblies and components. Basic requirement. You should know these all things. If you don't know, very difficult to get the job. Okay, they will ask the questions on the same thing. Tools recommended is the ANSA, Alter, HyperMesh. Job role or the description. see, they will mention about the machine frames, okay, and then the machine PIW subsystems, as I told, includes property and material assignment. Very important, guys. So if you mesh the model and if you didn't assign the proper material and the properties, um, it will be under a lot of issues. Yeah? Machine sheet metal components and the solids. You need to check the quality mesh. Quality check is very important, and then you need to check the model. And they will evaluate it, and then they will proceed further with the validations. Yeah, this is the model. And when it comes to CAE engineer, C analyst and C automation, C analyst automation, we call it. Yeah, this is the foremost job in your career, we could say. So the package will start with 8 LPA or 7 LPA if you're directly getting into OEMs. Yeah, and then it might go up to 18 LPA and then 25, 30 LPA. It depends. Yeah, so that's required. You need to know about analysis, static and dynamic simulations, linear and non-linear dynamic simulations, explicit analysis, NVH, durability, automation, yeah, and then model debugging skills, optimization, coding also. See, automation engineer, so you should know about the Python scripting also that you can implement the automation in it. Let's say I want to do some automations that I want to tell everything, so you know the coding so that you can just particular process your simulation or validation. Yeah. In short, what I could tell you is if I just want to post process the results, automatically the hyperview should open, and then it should load the stress and displacement, and then it should give me the graphs, and it should also plot the stress strain curve for the non-linear analysis. And yeah, this is what it should be. How you want to strip it. Simple. Yeah. Tools known. So as I told, LS-DYNA, Abaqus, Obstruct, ANSA. I think non-linear. Constant is important everywhere it is used. Well, job role I told you, debug the model, post processing it, result exploring, and the counterparts. You should be best in the communication skills. Very important, guys. If you're weak in communication, you're gone. Better go through these spoken English sessions and try to improve your communication skills. Yeah? And then running crash NVH jobs and interpret the results. Very important. If you're failing to do that, then you're gone. You'll be fired on the spot. So next, technical coding for the automated process and the methods also important. Yeah. Now this is all about the job roles, guys. Now you already got to know what exactly you need to do if you're a fresher. What would be the career options for you? You got to know that. Now, we'll start our mastery in CA from the scratch, starting with the history of EV and FEM. Yeah, if you see, we have the brief history. I could able to graph few things, not everything. If you want to have the more details, please refer some of the FU books. But whatever it is possible from my side, I try to extract it and put it forward so that you can understand everything. Yeah, let's go through this. First thing is, so when exactly the FE comes into picture, the first paper that is stiffness and deflection analysis of the complex structures was published in 1956 by you know we have the Claw and Martin and Top. Okay, so we generally consider this one as a birth of the current few finite element methods, we could say. Yeah. Now, after that, in 1960, Ray Glock uh, he termed the term called finite element. Yeah. So very important. So Ray Glock was the person who just used this terminology. Finite element. After that, there was a program. The currently we're using national, right? So in 1916 only, they started developing programs to run this kind of analysis. Yeah. Invention of programs in 1960s only. And then there is a current approach. What exactly they do is they divide the domain into a finite triangular subregions to solve the second order elliptical partial. differential equations in short. So it is mostly used for the torsion of a cylinder during that time. Then later, this contribution was very important and revolutionary. This, what exactly they developed the partial differential equations. Okay, you could see the names of them. Uh, Relay, and then we have the breaths, and then Galler. So these all together they developed this partial differential equations to solve the large body. We'll see that in detail next. Yeah, and then later on, the finite element method was provided in with a publication by Gilbert. Then this is started used by different industries in the electromagnetism, dynamics, okay, structural analysis everywhere. They started revolutionary, and everyone started using it and run the analysis and validate it before doing the physical testing. So physical testing will take a lot of money and time. Help us a lot to save the money. Now, what is finite element analysis or FEM? Could see the definition here. Finite element analysis is increasingly popular method used to solve problem in static structure analysis, dynamic, vibration, flow, and heat transfer, and many more physics also. In short, this finite element analysis is used everywhere. So, for example, a classic mathematical method considered a differential element develop a governing equations. Okay, usually in the form of partial differential equations. You're hearing this word again and again, right? If you're a fresher, that is all what you might see also. But you need to know about this partial differential equations. Very, very important. Yeah. I mean, like if you consider a real life scenario, real life problem, so how gonna exact all that? Say, want to obtain an exact solution for any of the equations of a complex geometry, practically you can do it, right? It is very difficult using the boundary condition, solving it only for 1D elements we could do it, but when it comes to large components, how it is possible? For that, this FEM method is viewed as a simple method where what it does is it approximates solutions for the partial equations, and it will solve with respect to the programs and give the results in the right? And you convert it into the stress or strain, whatever it is. Yeah. Let's see in detail how it is going to help us. Finite element formulation. A solution for a field variable satisfying both boundary conditions and differential equations is unknown in general. Right? Let's say you want to define a boundary conditions where you want to fix it, where you want to apply the load, right? So for that, how the equation is going to form, we don't know. So for that, we begin with the trail solution. So what is trail solution? It is just to use to satisfy the boundary condition in short. Boundary conditions is equal to zero in this one. Yeah. Now, for example, when it comes to trail solution, it does not satisfy the differential equation exactly. Okay. There will be a small error with respect to differential equation. How to gonna correct this? So for that, we have this weighted sum of the residual, we call it. So this comes into picture. We add that approximate constant to make the entire solution equals to zero or render to zero. Okay, it is quite difficult to grab it now, but if you go through okay, so you will definitely understand it. Next, what we do is we try to discretize the domain into several segments. Okay, called as finite elements, and use several piecewise continuous scale function. What are these continuous scale functions? Now, when it comes to trail function, it's just a segment in a particular. For example, let's say we want to solve a particular element inside the geometry. So we take it as a main function. Okay. And then in that, for each segment, we define a shape function. What is shape function? In short, if you consider any of the elements, okay, if you don't know about the elements, there will be types of elements. I'll just show you this. It's the 1D element. See, these are the 2D elements, trias and the quads. Second order element, first order. First order will have only the triangular element. So the first comes to second order, having six nodes. Okay. Now these are the 3D elements. We have the tetrahedral, hexahedral, okay, quadrilateral elements. Right? If you consider this function, what exactly do is, okay, we define the interpolation. Okay, we try to calculate the results on each of the key points, call it as nodes in the element. Let's say if you consider triangular element, on the three nodes, we have to extract this. Okay, and then we try to form a stiffness matrix for this element. Let's say, in short, we have the shape function for each element. We try to get the weighted sum for the domain residual, okay, for each element. Then we sum up all the elements to get the again weighted sum for the entire domain. Using weighted sum, why? Because we consider one constant, approximate constant to equate it. For that time, it as weighted sum. Now, once we have this, all the weighted sum in the form of the matrix, or it has a stiffness matrix, and so once we have the shape functions for that model, on each and every node, having the boundary conditions and defined that we need to solve it, right? So that we call it as stiffness matrix. We call it as a matrix. So now to solve this matrix, we define a programs or develop programs like ANSYS, mass Abaqus, this structure, right? And these programs will solve this matrix and gives us the results in the form of the instrument and convert it to different form. Now, that is what I explained. Okay, now let's directly get into the whatever the expression I given. This is for each and every field. Okay, let's say transfer, structures, flow, and then electromagnetic analysis. So this is the scenario for now. We'll see the exact process. What exactly we do in this at the end. Assume we have the Young's modulus, Poisson's ratio, and density defined to the this is a rectangle. Consider the thickness is 5. Now we define the material properties. Young's modulus very important. If you get now static analysis until the elastic limit, you will have all the uh, stress proportionalities, right? And so getting it, they are satisfactory for that component. If it is going beyond that, it'll get for a particular component, the 230 or 240 is the uh, maximum elastic stress which it can withstand. To go beyond that, then definitely the component is not stable and it is going beyond elastic. We can consider what is Poisson's ratio, change in line to the original length, and the density, the measuring mass of it. Now we define the material for the component. What next? We define the boundary conditions. So here we apply the fixture where exactly the component needs to be fixed in a critical scenario, and then apply the force and another direction. So it might be a simple, it might be complicated, okay, it might multiple loads applied here. But here is a simple scenario. Once I have fixed, once I have just trying to pull it, I have just defined boundary conditions. Next, the next step, we try to disguise the model in the form of the small elements called as mesh. What is mesh? Creation of complete model in the small elements. Okay, that element will have nodes depending on the mesh. Okay, four nodes depending first order, second order. This is what we do in the meshing. Things. Once we do that, we try to solve the residual functions for each and every element on the nodes built up of the results and so equation. And that particular stiffness matrix for that particular element will be summed up for each and every element, a global residual stiffness matrix. Okay, that matrix will be taken for the analysis. Any of the programming will solve it and get the results. Let's see, we have the shape of the model, we have the nodes on that, we solve these equations. Okay, we will use partial differential equations. Again, it is a big thing, so we'll see that. Obtain the results, solve the results. We're gonna obtain the stress or strain or the factor of safety and the distance. So, first, what we get is we get the displacement. That form of x comma y, if it is in 0, and that will be converted again to the stress, strain, or the factor of safety and other required things. This is what the complete process for the CAE. And that's all right. If you have any doubts, so please leave a comment in the box and then read just out. So you have to grab everything. Next, we'll see the governing equations. So what is partial differential equation? How it is formed, right? For that explanation first, we'll see, right? We have the variation method. We have the Galerkin's weighted residual method. So I was doing right. Weighted residual point. So this is, let's see, first one is the direct dividers. Short, this is a strong element form, we call it as a strong form of the, okay. It's the equation for the direct method. So it will considering modulus into a moment of inertia. Then boundary conditions. So we try to solve it to get the results. But this equation is used only for the beam problems in CREO of 2D in short. Okay. For the complex components in short. Yeah. Now these are also the differential equations. Now when it comes to initial method on Galerkin's weighted residual method. So these are the weak forms of integral forms. We use the integral forms to solve them. Okay. So we use the approximate solution for equilibrium equations. Although the results we get it in the end is not 100% accurate, right? So 85 to 80%, the 90% we can assume, but the results you're getting not at all 100% accurate. That is what you might, and that to achieve this 80% accuracy to resolve the analysis. Now, let's see what is variational moment. In short, this variational method works minimum potential energy. When it comes to potential energy, you already know, right? Strain energy, work potential. Okay. Strain energy, strain energy stored in structure, okay, and then work potential, a negative work done by the external force. Okay, if we combine these two, so what we get is potential energy in terms of displacement. We try to minimize the potential energy. So this is what the variational method does in short. Yeah. So this is the equation. Total potential energy is equal to strain energy plus potential energy of external force. Now we'll see the Galerkin's weighted residual method. This is the very important topic here. This is what we use everywhere in everyday life. So here it is. So this method is the powerful way of finding approximate solution to differential equations. So we use piecewise strain function here to approximate these peak forms. Okay. We call it as the Galerkin's residual technique. Yeah. Now, so weak forms and the piecewise strain functions are the approximate solutions. You already know this. So, well, just example. I'm not going to it. I'll try to explain in short. So if you consider L as a boundary, the image you could see, right? And then we have the rho as a domain. Okay. We consider this as a problem. How we solve it? So assume we have the problem. Okay, example. Was try to use as failed solutions. We have f of x, which is equal to c0 plus x plus c2x squared, like this is the great function, right? So if you want to explore this to mathematics, Fourier, everything, yeah. Then, so what we do, we take this one when we try to apply the boundary condition. Okay, so what exactly we do here? We try to determine the C1, C2, C0. So how do we do it? By using the Galenkin's weighted method in general. So we try to find the unknowns, that is u. We assume the approximate solution of the form. This is the one. Okay. This equation will be used, just I showed you, right? And then here you could see Ci is the independent coefficient. Okay. By the weighted residual process, Ni are the pre-selected such that displacement should satisfy all the prescribed boundary condition. Okay. Now, if we consider this equation, so I is equal to 1 to n, and then domain we consider, we try to find out where wi which is equal to ni, okay, the residual function. We try to make it to 0. Yeah. So, for example, this is the equation. Okay, considering the weak form of the residual statement, this is what the equation we have it. And then, so this is the differential equation for the axial load. We consider this and we try to fit it into the formula, and we exactly get this. Okay, E differential du by dx square plus dx, which is equal to 0. Yeah. And now, so this is what we try to solve it for each and every element when it comes to displacement on these nodes. This is the matrix U1, U2, U3, U4. We try to calculate for all the nodes, and then we feed this into this equation. And this again equations will be fed into the this equation here, and from this we get this one. Okay, stiffness matrix plus displacement. We solve it for the force, and we get the displacement. Okay, displacement is equal to inverse of stiffness matrix plus force. Yeah. So this is how it is. I have tried to explain this in a better manner in the previous videos. If you go to my YouTube, refer everything. But right now, due to time constraint, I'm not going in depth. So it is just taking you through basics of it. I'm not taking you through the equations. If you want to know about these all things, kindly refer any of the any books, or else you can refer my previous YouTube videos. Also, you can refer on those videos also. Yeah. Now, for example, so let me just try to summarize it here. I'll try to explain this one here. We have one D element we can right. So, for example, a stiffness matrix problem. Okay, needs to express in the form of the partial differential equation. Okay. Now here we have the P of x load is along this direction. It is moving x, and here I'm just trying to move this one with respect to P of x plus delta x. So change in length. It does. There is total length. This is the force applied. This is U1 and U2. Okay, if you consider this example, axially loaded elastic bar, we have it. So if we consider the definition of the stress, a strain, and the Hooke's law stress, which is equal to force per unit area. Okay, so if you consider this one here, the P is the force and length into, if you consider the area, will be having the stress. Okay, strain change in length to the original length, d delta. We consider delta L also change in length to the original length. This is strain. What is Hooke's? Under the elastic limit conditions, stress is directly proportional to strain. So we have this in stimulus or this proportional limit constant we call it. So if you double stress, definitely strain will also double under the elastic limit condition, guys. Okay.
the hooks will only satisfy for the elastic condition. Okay, proportional range. Okay, we'll see that. I'll show you later also. Now, taking these all equations, let's say if I want to solve for the derivatives for u, okay, here P force, which is equal to stress into area equals to area likewise. Okay, here if I consider this equation, stress which is equal to Young's modulus into the other strain. Okay, A is the constant. Okay, we take it, and here derivative of change in length to the original length. Again, u2 minus u1. Try to solve for the small x by using the integral form, partial differential equation. Assume limit x tends to 0, and if you try to prove this here, let's say how this came here, positive and negative direction forces I'm considering. For example, this is moving negative, so minus p of x, correct? And then positive is this p of x plus delta x plus force I'm applying from x to x plus delta x, okay, in the form of integral f of dx. If I solve this one with respect to delta x tends to 0, now this is what it comes. So p of x, this one, and here delta x plus x, which is equal to, taking it here, dividing it here. Okay. Now dp by dx will happen. Okay, this is what it is. Plus x. Now what is p here? We have it here. AE, change in length to the original length, du differential of this one plus this one. In short, force, which is equal to stiffness matrix into constant. Okay, we call it as change in the original length. This is how the equation forms. Okay, partial differential equation. Now, for example, this is the example. Let's say I have the stress of 300 megapascal and of the strain that is 0.00.5. And if I want to calculate the Young's modulus, what is the formula? If you consider the Hooke's law, that is stress divided by strain. Okay, and then 300 divided with this value is 215 kilo, and then 200 gigapascal. Correct. Likewise, we try to solve the problems. Now, let me just take you through the different types of general equilibrium equations. We have the general equilibrium equation for such and everything. So this is mass matrix where we have it, and this is the velocity plus we have the damping matrix plus sorry, this is acceleration and this is velocity plus stiffness matrix. And then this is the displacement, which is equal to applied load. If you want to solve for static analysis, these two will become zero because there is no acceleration applied there, there is no velocity, only the displacement will be there. So stiffness matrix into displacement, which is equal to load. Yeah. When it comes to static analysis, this is what I could show you here. Now, buckling analysis is formula completely different. We have the K, and then plus we have the eigenvalue lambda, plus we have the KD, that is differential stiffness for the geometric stiffness. Yeah. Then the eigenvector, which is equal to eigenvalue plus load. Okay, where we try to find out the buckling loads and buckling analysis, and we check whether the component is going to buckle or not. For the vibration analysis, we take this one. So we now again the same. We consider the mass matrix where we'll be having the acceleration into account, and then we try to solve this one. Okay, I hope this is clear for you guys. And yeah, this complete equation will be generalized, and then if you want to do the analysis based on your requirement for the static, buckling, vibration, dynamic, linear, non-linear, we try to change it, yeah, based on the acceleration values and the velocity values and the displacement values and the boundary conditions. How do we solve the engineering problems? We got to know everything, right? So now there are different methods. One is the analytical method, numerical method, and the experimental method. So currently we use the analytical method and the numerical methods. Experimental method also we use it, but the costlier we try to depend on these. Then we test it for one component. Then we make the decisions. There are different types of numerical methods again. So one is the finite element method, which is predominantly used. Boundary element method, finite volume method, and we have the finite difference method. Right now, when it comes to finite element method, what exactly will happen here? We try to calculate the results at the nodes of each and every element. Okay, let's see if we have this one. Each and every elemental nodes will be considered and the results will be extracted. When it comes to boundary element method, the calculations are made at boundary nodes and the results are interpolated for the elements. Okay, for example, if you consider heat transfer problems, we use that. Now, finite volume method. So, what exactly we do here? It's based on the Navier stroke equation. So if you want to get into CFD domain, you need to know about the Navier stroke equation. It's a complete different domain. You need to know much about it. So left track or of left left track. Okay, Navier stroke equation, laminar flow, turbulent flow. Okay, what is Reynolds number? A lot of things will be there in that. Now we have the finite difference method where we try to use the Taylor series to solve the problem. Yeah, I hope this is clear. Now when it comes to CAE analysis types, so we have the FEA, and then we have the CFD, then we have the multi-body dynamics, we have the thermal analysis, we have the electromagnetic analysis, and the optimization analysis. So as I said, guys, we can focus on FEA or else CFD or else optimization or electromagnetic analysis or the thermal analysis and make your mastery in any of the domain or all the domains. Quite difficult to make the experience in all the domains. You're expert, you can even try that. But I would recommend FE is the most prominent, and even optimization and the thermal analysis and CFD can refer as the initial stage. Now, when it comes to FE analysis, we have a static analysis workouts. What we try to do is we solve the equations under the elastic limit and we try to extract the stress, deformation, and dynamic analysis. Okay, here we try to solve the equations in the form of the input of the vibration we consider. Okay, and we try to extract the dynamic responses such as the natural frequency, mode shapes, and the damping ratios. Okay, and then we have model analysis where we try to check for the mode shapes and the frequencies, how it is going to happen, and mostly we use it to how the component is behaving at a particular frequency, and accordingly we try to solve results. And buckling analysis. So what exactly we do? So we try to check whether the component is going to buckle with respect to the given load. If it is buckling, then we try to optimize the component to resolve that buckling. Now the last one is the fatigue analysis. So what we try to do is the repeated loads will be applied. With that, how many cycles it is going to withstand. Based on that, we do the durability analysis and get the results and make the decisions. And the heat transfer. So here, with respect to the temperature distribution and heat flux, we try to extract the results in the form of temperature distribution and the heat flux, and we try to optimize the results. Next one is the non-linear analysis, where we try to get the results beyond elastic limit. Okay, where we try to predict the plastic deformation and the material failure, and try to optimize the component and get the results out of it. Yeah. Now, when it comes to non-linear dynamic analysis, we have the model analysis, response spectrum, time history analysis, harmonic, and the random vibration. It is again completely a deep dive. I'm not going to take you through that, guys. You can refer some of the videos, or else you can refer my YouTube also to go in detail. Now, when it comes to structural analysis, this is what you need to know. When it comes to linear, we have the linear static analysis and linear dynamic analysis. Okay. When it comes to non-linear,
We have the implicit nonlinear analysis and then the explicit nonlinear analysis. Implicit, we try to apply the loads for the longer event and we try to extract results for the small deformation. This number of contacts in the simple material model will be having it here. And static stress, loading and the gravity loadings will be taken into account here. When it comes to explicit, it's a short event. Okay, within a couple of seconds, the load will be applied and large deformation will be there. How the component is going to feel under the plastic limit, and then we try to do the analysis, get the results, and optimize the component. For example, crash, drop test, explosion, board strike analysis, all will come around. Come when it comes to non-linearity, we have the material non-linearity, geometric non-linearity, and contact non-linearity. So we need to know about each and everything. So when it comes to non-linear analysis, you need to know what are these. Do we solve this? If you want to solve the non-linear analysis, you need to have the non-linear material properties, geometric non-linearity with respect to geometric shape, how this linearity is going to impact on your model, that you need to analyze it, and the contact also, how you need to define the contact. Okay. Next, so when it comes to implicit and explicit analysis, just a simple example. So if you want to solve the normal static structure analysis, you just apply code. There is when it comes to implicit, it is exactly in between static to explicit. So what we do here is, so we try to solve the results exactly in between that. We try to extract the zero for certain value we apply with respect to a certain thing, and we try to extract the solution, and we call it as a quasi static. When it comes to explicit, we try to apply the load within a couple of seconds. The large deformation, we do not analysis of that. So where exactly implicit lies between explicit and the static. For example, forming analysis, sheet metal forming, we do right. So there we follow this. Okay, where uh, try to get the plastic deformation right when it comes to bending. So that bending is necessary. The plastic deformation is necessary for us. So that is called as the static, not the non-linear, but in between static and dynamic. So in short, this is what exactly the difference is. So what we do here, impact and fully dynamic, we try to apply one load, like okay, so we apply. But here in past, we try to apply load from zero. So let's say point 0.1, point 0.2, point 0.3 like this up to 1 increment in order. The load will be kept constant here. So slowly apply the load. When it comes to deformation and the forming, slowly load will be applied and then at the it will be the full load. Yeah, that's clear, right? And this is about the properties. When it comes to CA, you need to remember mechanical properties. We have the yield strength. We call it as it's a maximum tensile stress material can withstand. Okay, before the permanent deformation. So whatever the region it is that behind it, it is all safe. We call it as the proportional limit. Ultimate strength, maximum stress before the failure. Okay, this is the failure point. This is the ultimate point. Here, the component will definitely fail. Okay, and then the fracture point, or it is where the failure occurred. This we call it as the failure point. What is this difference? Okay, how a component resists exactly deformation when the load is applied. Okay, that is what we call it as stiffness. How stiff the component is for the load. Hardness, resistance to the localized deformation. So I think we have done the CharP testing. Okay, remember right when it can so you might have done CharP or the in-house labs. So we do this hardness testing. Yeah, so that is what it is. Once you apply a load at a particular surface area, so that is we call it as a hardness test. Next, we have the resilience. What exactly we call it as resilience?
are defined as the ability of a solid component to absorb the energy under the limit. So this is what we call it as this region is the yeah. So the how you're seeing this is for the tactile component. So in more detail, you could see when it comes to stress strain to the brittle material, it comes here at a particular point. Let's say 300 megapascal. The component will fail small strain and patch. When it comes to ductile, there will be large deformation. Okay. Now this is a stress strain curve. For example, if you take E, this is called the Hooke's law region. Its stress is 50% strain. Then we have the elastic limit. Okay. This elastic region will start. Okay. This is the yield point up to here. It's fine for us. Okay. And then from here, ultimate strength here directly the complete failure will happen, and then this is the fracture. This is the plastic region, guys. This is the plastic region. When it comes to materials, we have different materials. One is the elastic material, the plastic material separately, and the elastomers. So you need to know about these materials and how to try to explain that once we can interpret that data. Isotropic material, autotropic material, isotropic materials. For example, isotropic we have the steel, okay, and then when it comes to glass, glass, everything are the isotropic. When it comes to orthotropic, okay, so the loads are directionally. Okay, for example, wood, crystals and rolled material are the orthotropic. When it comes to isotropic, so these are directionally dependent. For example, the cloth rubber also. Plywoods, if you consider, uh, they can withstand the loads along a particular direction. If you try to apply the load along another direction, they might fail early. Okay, so use most of the material properties which are needed for the linear and non-linear. When it comes to static, we use modulus Poisson's ratio, most predominantly mass density, mass calculation. Okay. Now, non-linear contact, if you want to try, so we define these all the parameters. When it comes to fatigue, we use the Young's modulus, and then Poisson's ratio, mass density, and the stress versus number of cycle curve for the fatigue. Non-linear material, we need the stress strain curve and the material data also, non-linear material data. Star means only for the analysis, not for everything in short. Yeah. For linear dynamic model frequency analysis, we do need the mass density. Yeah. Now, you stresses, types of stresses. If you remember, okay, we have the normal stress, we have the shear stress. Okay. So when it comes to now, this is the principal stress also we have it, then the equivalent stress also we have it, right? So now you consider stress tensor, you can see if I consider a particular x direction, sigma x6, sigma xy, sigma x will be the stress tensors. If you want to create a matrix out of it, this is what it is. Sigma x, sigma x, sigma x and then similarly for y and z directions. This is how the matrix will be. Enormous components. Yeah. So normal stress, sigma xx, sigma yy, sigma zz. Okay, x, y, and sorry, z, y, and x are the normal stresses. When it comes to shear stress, you could see sigma xy, sigma xz, sigma yz are the shear stresses. Hope it is clear for you guys. Now, why I had explained that one, how the component is going to be. For example, for the ductile material, if you consider that feel at shear stress, okay, you can see like this, for the shear. When it comes to brittle material, they will fail at normal stress. So this is normal stress. It will be like this. Okay. Now, principal stress are solved as eigenvalue and used to deal with the brittle materials here. Eigenvalue is what is equivalent stress, very important. So we try to extract results, right? Equivalence one minus stress. So what it is, we try to evaluate result for all the stress tensors and give one equivalent uh, value. This value represents the material status of the ductile materials. When stress is usually acting a scalar, okay, shear stress energy per unit volume measured different point in a stress material. If we consider this one, we are not going to consider all these stress tensor. When it comes to equivalent stress, right, one average for that particular element. Yeah. Now, what is the main difference between linear and non-linear analysis? Very important, right? So when it comes to a linear analysis, okay, for example, if you consider a spring is extended statically by 1 meter and the load is 10 Newton, okay, and if you want to extend this to 2 meter, when it is going to happen? When you have the load, stress is strictly proportional to strain here. Okay, I hope you got it. So now this means that linear analysis flexibility of the structure need only the calculated once. So you don't need to do the analysis every time. The analysis once you have the stiffness matrix, that is more than sufficient. You can use it for all the solutions. But when it comes to non-linear, it is not the case. We do it for the forging, stamping, crash test, and the rubber analysis. For example, let's say for all the physics exhibits non-linear, linear static analysis can be performed for the purpose. For example, if you consider non-linear, for each and every loop, you need to change the stiffness matrix. Okay. Let's say for the linear spring, stiffness is constant. Just like displacement first. Now, when it comes to non-linear, you can see the stiffness will be different. Okay, it will change. So now you can see since the stiffness is now dependent on the displacement. Okay, what exactly will happen here is flexibility will not be no longer will be identified outside load. Okay, now we need to calculate each and every stiffness matrix in the non-linear analysis. So again, for that, this particular solution might not be available for simple softwares like SolidWorks simulation is quite not that uh, good for the nonlinear analysis because that algorithm is not going to support for the complex nonlinear and dynamic explicit analysis for the automotive industries. For small scale industries, you can do that, but when it comes to automotive industries, it is quite difficult. Yep. I hope it is clear. And yeah, I would like to conclude the session here. This is most of the basics we have covered. So from this session, I hope you got to know what exactly you need to do as a fresher, or if you're experienced. We try to go through the basics of FEA, how it started. We already seen some types in FEA and CAE field. So what are important, how we need to start a career, yeah, and then if you're uh, willing to get the basics also, we try to in the basic requirements. We basics of FEA and FEM. Yeah, in the later sessions, I'll be taking you through the examples. So structural analysis basics will cover, and then we'll jump into the Crash and NVH analysis in depth that people can experience on it, and that might be helpful for you to gain the experience and get into any of the OEMs or medium scale industries to get a job. Okay. And whatever the course we are providing, these webinar are free. Of course, you don't need to pay anything. So the live link will be provided. You can pick it up and share it to your colleagues and friends. Make sure you can utilize it properly and gain the experience. And also, for just from our side, if you haven't subscribed our YouTube channel, please do subscribe it. And we have already a lot of content available for uh, simulation, SolidWorks simulation, HyperMesh, and Abaqus, ANSYS, CFD, ANSYS Print. We have all the playlists available so you people can refer them. Yeah, and then we have WhatsApp community. Please do join it. So you'll get the links. I think you might have got it if you're following us on LinkedIn. If not, please do refer our LinkedIn page, Technocraft Academy. You will definitely find the link and join our group. If you want to have the personalized training, please do contact us.
will help you out with that code. Yep. And these webinars will be conducted every week. And then don't forget to join upcoming sessions also. Well, thank you all for joining, guys. See you in the next session.